Hello everyone, to whoever's watching this. Here I'm just gonna give you a very quick elevator pitch for my new algorithm, my new blind source separation algorithm. It's called universal component analysis because it's able to separate Gaussian, normally distributed data. So here's the basic problem. Gaussian data cannot be separated using higher order statistics like ICA does with non-Gaussian data, say using kurtosis or skew or whatever, because Gaussian data, it lacks any of those, distinguishing characteristics. And so here's the solution. Instead of sort of directly optimizing for a higher order statistic, we use a likelihood-based algorithm that doesn't rely on that, but instead it kind of makes a best prediction of where the original solution is in the set of plausible solution spaces based on the shape of the solution space itself. The space of mixtures of reconstructions that do not correlate with each other, the orthogonal rotations. And yeah, let's get on to it. So if you were to map out the space of orthogonal rotations, it looks a little something like this, where there are both flat and curved regions, flat, steep regions, and sort of a transition space in between. This is an example of a very strict example, a very severe example, where you have a very flat area, a very steep area, and a very tiny transition region in between. Now, you might go ahead and say, well, the original solution could be anywhere along this curve. Well, technically that's correct, but based on a probabilistic sense, it is very unlikely that the original solution is going to be located in these either very flat or very steep regions. Very, very, very most likely it's going to end up in this sort of transitional space. Here's why. I don't know if this is quite a established statistical principle, but here's my conception of it. Consider a multivariate set of data and a set of criteria that depends on such variables as to produce a function. Then we have the following principle. Given, without any extra information, that a data point satisfies such criteria, it is most likely that that data point is going to appear along the regions of the set of possible solutions where the slope is close to 1 with respect to all other variables affecting that function. Here's what I mean. Here's kind of a demonstration. In this kind of plot, I've highlighted the set of possible solutions, and this is just the region where the reconstructions do not correlate with each other, because that is one necessary condition, a necessary condition but not a sufficient condition for the reconstructions to be equal to the original sources. And I've separated it into 3 rough regions. One is flat, one is steep, and one is sort of in between. Now, these flat and steep regions, they are less likely to include the original solution, because if you look at it, for the flat region, the flat region only you're only going to end up in the flat region if your y-axis, if your second data is in this very restricted range. And the same thing goes with this steep region, this will only show up. You're only going to end up in this space if your first data is between this similarly restrictive range. Now contrast to this small slice where it's sort of a transitional space. You have fairly forgiving ranges for both data values. So as a result, this sort of solution, this possible solution space, it is more likely to hold the original source than is predicted just by its length alone, because it does not rely on very narrow ranges of parameters. I hope you kind of understand that. I'm kind of rambling at this point. I haven't really prepared this presentation, but I hope you understand my logic. Now, how does UCA work? It finds a point along the orthogonal solution space where the slope is 1 with respect to all independent variables, or -1, absolute value of 1, doesn't really matter. And this is sort of where that kind of trade-off between having a forgiving x-axis and having a forgiving y-axis is kind of maximized, and that is why the space where the slope is 1 is most likely to contain the original source. And this is just a little aside, but this is my idea as to how this algorithm would be most efficiently applied. Right now it's kind of messy, kind of slow, but here's how it would ideally work. So you kind of find that middle boundary, that center point between these, these transitional points we have, and this center point can be found simply by taking the edge cases and using that kind of as a proxy for the center. And then once you find that center, you kind of optimize along one dimension, and that one dimension will be sort of diagonal to all the axes. So once we do that, wherever we find the local minimum, that is the point where the sort of slope is going to be 1, and that reduces this problem to a one-dimensional optimization. Of course, like the time complexity is not going to be O of n; it's going to be polynomial at the very least. Now, here's one extra feature. The beauty of this algorithm is that it's not just probabilistic, but if we actually kind of tweak the data we're given, we can actually have it so that it kind of infinitely converges to the true solution space. So here's what I mean. In the following sort of plot, we see that the slope is close to 1 across the entire space. So here's close to 1, here's close to 1. It sort of varies here and there, but overall very close to 1. And this is a big problem, because then, the original solution could be, it could be really anywhere across this map. We don't really have a very good guess as to where it might be, and that's a that's a huge problem. So we transform using PCA the original mixture, which is quite a poor mixture, and we transform it into one that is more steep. And so we've transformed, simply by taking a PCA transformation and then combining it in a way as to exaggerate the differences. We've created a very, very steep, very contrastive mapping. And so in this sort of reformulated solution space, the kind of range of likely solutions is much more restricted to this very small point. Wonderful. And so that's really the crux of the algorithm. To rehash it, to rephrase it. Step 1, perform PCA and create a new mixture of PCA transformations. The more contrasting, the less dispersed the new mixing matrices, the more accurate the final reconstruction will be. And it will converge to the original. So I think it's like, as you kind of, sort of maximize this objective, you're going to get closer and closer to the original source. And then step 2, find the point of the slope where the space of the zero, the orthogonal rotations is as close to 1 with respect to all of the axes of rotations. We've covered this. Note that there will be many symmetrical points. For example, here we obviously have this point and we have this point. We could use either of them as a solution, and the only difference between them is that they're just going to be different orders. You're still going to get the same original reconstructions, but they're just going to be sort of permutated in order. And then that's it. You take the implied angle values, the angle values of that slope, and then you feed it into the reconstruction, and that will give you, the best possible guess of the original original sources. I will have a separate video, I think, where I sort of run through my code, my unoptimized code, and give you a demonstration, a 2-dimensional demonstration of how the code works in practice.